Hello, this is section 7.3 trigonometric substitution. All right, before we begin, let me have a quick review on some trigonometric functions that we have to be familiar with. Mainly, it's when working with a triangle. So when we're using our trig functions in a triangle, doesn't matter how you draw it or how you label it, as long as you have a 90-degree angle. Now, when you're working with your trig function, sine, cosine, tangent, and the reciprocals, we will use an angle theta. Theta can be any of the angles that are not 90 degrees. Doesn't matter which one you choose to be theta, as long as you stick with that being your theta. So for this problem, let's go ahead and make theta this problem here. And let's say I give you something like sine of theta is equal to x over 3. And I ask you to find all the lengths or label all lengths. Well, if we do that, remember sine is opposite over hypotenuse. So the one that's opposite would be 3. And our hypotenuse is always the one that's opposite of the 90 degrees. So opposite over hypotenuse. I really put that wrong. Opposite would be x and hypotenuse would be 3. Now to find the other length, remember we have a 90-degree triangle, so we just use our Pythagorean theorem. A squared plus b squared equals c squared. Remember, c squared is always your longest side, which is your hypotenuse. So we know our hypotenuse is 3, so we have 3 squared is equal to x squared plus whatever b is, b squared, right? Or our unknown squared. So we need to solve for b to find this other unknown side. And it doesn't matter which one you label A or B, but C is important. C must be your longest side, which is your hypotenuse, which is the side that's across from 90 degrees. So we have, we subtract x squared. So we have b squared equals x 3 squared minus x squared. So we have b is equal to the square root of 3 squared is 9, 9 minus x squared. So we have the square root of 9 minus x squared. So this way we can figure out any other trig function from here using these pieces. So if I want to know, for example, cosine of theta, well, cosine is adjacent divided by your hypotenuse. Adjacent is the side that's always next to it. Adjacent would be 9 over x squared. I'm sorry, square root of 9 minus x squared divided by your hypotenuse, which is 3. And you can use your side measurements to find sine, cosine, and tangent. Similarly for cosecant, secant, and cotangent. Now something else I need to review for this section is what if we want something in terms of a different variable? Let's take this sine theta equals x cubed. And say I want to, for example, solve for theta. Meaning you want to get theta by itself. The way we undo that sign is by multiplying or applying sine inverse to both sides. So sine inverse, this and the sine inverse, they're inverses. So you're left with theta is equal to sine inverse of x over 3. And we do this because sometimes we need a function to be in terms of a different variable. So here it'd be in terms of x because our argument is in x, right? All right, so this is a quick refresher on some trigonometry because we're going to need to be familiar with this. So we need to be familiar with finding the sides of a triangle and solving for theta. Okay, let's continue with trig substitution. All right, so when do we use trig substitution and why? Let's read from our notes. Consider trying to find the area of a triangle or an ellipse, such as the integral of the square root of a squared minus x squared. Note that we cannot use u substitution because we don't have an x to replace with the dx. Since we would have to let u equal x squared and then du be 2x dx, so to continue using u substitution, we need an x. Using trig substitution, we change our argument variable to theta and make the substitution x equals a squared times sine squared theta. And we can then simplify as the following reads. The square root of a squared minus x squared turns into the square root of a squared minus a squared times sine squared. We can factor in a squared to have the square root of a squared times 1 minus sine squared theta. And then we can apply the square root so that we're left with only a in cosine theta. Notice the difference between the substitution u equals a squared minus x squared, in which the new variable is a function of an old one. The substitution x equals a sine theta, the old variable is a function of the new one. We can make the inverse substitution x equals a sine theta provided that it defines a one-to-one function. This can be accomplished by restricting theta to lie in the interval of negative pi over 2 to pi over 2, for example. And we use this restriction because we have sine. All right, the remainder of this section is working with examples and learning how we can work with different types of situations using trig substitution. This is our chart that we're going to use for trig substitution. These are the only functions that we have to work with. Now, usually we'll have a radical of some sort, and we're going to have a number squared minus x squared, your variable. If so, your substitution you're going to use is x will be a sine theta. And of course, we're going to use that restriction for sine, negative pi over 2 to pi over 2. And the identity that's going to come in handy is your Pythagorean identity 1 minus sine squared theta equals cosine squared theta. And we do this because we want to be able to apply the square root and move forward. But what if instead of a minus, we have a plus? Well, then we use a different trig substitution. If I have situations such as the square root of a squared plus x squared, then my proper substitution or my ideal substitution would be x equals a tangent theta. And our identity that will come in handy is 1 plus tangent squared equals secant squared. Now, what if the order is reversed? Remember, in addition, order doesn't matter. So if I have x squared plus a squared, that's still the same one. But what if I have my variable minus my constant, x squared minus a squared, all under a square root? Then my ideal substitution would be x equals a secant theta, and the identity that would come in handy is x squared theta minus 1 equals tangent squared. Now, as you read all of these, your constant a, the constant, which is your a, will be the number in your substitution, but it's going to be the square root of it. So the a squared will be the number that's squared in your integral in your problem. And remember, to get this number, this would be the square root of that. Alrighty. Okay, I think we're ready to try a trig substitution problem. Let's take a look at this example. Evaluate the integral. The square root of 9 minus x squared divided by x dx. Now, how do we know we have to proceed using trig sub? We know because if we try using u substitution, which I would probably always do my default, I would let maybe something like 9 minus x squared be my u. But then when you try finding your du, you see that you do not have an x to 1 degree. You only have that x squared. So this makes it so that you can continue using that method. But we can use trig substitution. And we see that we have that a squared minus x squared setup that matches our first option from above. So because of that, we're going to let x equal a sine theta. Or not a, the square root of 9 is 3, so we're going to let x equal 3 sine theta. X equal 3 sine theta. Now we still use the same practice that we use for u substitution. If we let x be a variable, we also need the derivative. So dx equals 3 cosine theta d theta. Okay, let's go ahead and finish off this problem. So let's go ahead and plug it back in. Now a lot of the work and the effort goes into that substitution, so I'm going to focus on the substitution only. I'm going to only focus on this part right here. The square root of 9 minus x squared. That's my only focus right now. I'm going to clean that up and then I'll go ahead and work with my entire integral. All right, so we said that x squared, well, the x will be replaced with 3 sine theta. So that we have the square root of 9 minus 3 sine theta squared. Okay, so this gives us the square root of 9 minus 9 sine squared theta. Let's factor out a 9. So I have 9, 1 minus sine squared theta. And then we keep the Pythagorean identity. 1 minus sine squared theta is cosine squared. All right, so we have the square root of 3 cosine squared theta, which gives me, oh, I got ahead of myself. We still have a 9. So when we apply the square root, we have 3 cosine squared theta. Cool, let's go ahead and plug that in. So let's see what we did. So our integral is the square root of 9 minus x squared dx. Let's make those changes. Okay, so in our integral, we have our numerator. Remember that square root? We clean that up to be 3 cosine squared. So we have 3 cosine theta. I don't know why I wrote squared. He took the square root, so it's not squared. 3 cosine theta. Okay, in our denominator, we have x squared. Okay, well, we said x is 3 sine theta. So that's just 3 sine theta squared. Last piece, what is dx? We said dx is 3 cosine theta. So we have 3 cosine theta. Theta. Okay, let's clean this up. So if we clean it up, we see that our 3's and our 9's cancel. Well, let's first square the denominator. So we have 3 cosine theta, and we have 9 sine squared theta, so that's being squared. 3 cosine theta d theta. We see that those 3's divide out with that 9. And we're left with cosine times cosine gives us cosine squared. So that we have the integral of cosine squared theta sine squared theta d theta. All right, well, cosine divided by sine. Well, sine over cosine is tangent, so cosine divided by sine is cotangent. So what I really have here is cotangent squared. Right, using our trig identities. All right, now let's look at our integrals and see which would be the best way to go. Well, we know the integral for cosecant squared, so let's replace cotangent squared using our Pythagorean identities. We have the integral of cosecant squared theta minus 1 d theta, and I can apply that integral. So that our answer is cotangent, negative cotangent theta minus theta plus c. And while we would think that we're done, remember, our question is asked in terms of x, not theta. So we need to go ahead and change this back into in terms of x. So change back to x. To do so, we have to use our triangle. So if we have a triangle, you can draw any 90-degree triangle. Label whatever side that's not 90 degree to be theta. What did we say? We said that x equals 3 sine theta. Okay, we need to find cotangent using this information. So if we divide by 3, we're left with x over 3 is equal to sine of theta. Remember, sine is opposite over hypotenuse. So we have opposite is x. Hypotenuse is the side across from your 90 degrees is 3. So this side is 3 squared minus x squared. So we have 9 minus x squared. Now we wish to find cotangent of theta. I remember tangent. Tangent is opposite over adjacent, so then cotangent is adjacent over opposite. The side adjacent to theta is the square root of 9 minus x squared. And the side opposite is x. So that would be our cotangent theta to replace here. But now we also need to find theta. So we need to take our argument that we created, x equals 3 sine theta, and solve for theta. Okay, let's do that. So we divide by 3, we have x over 3 equals sine theta. We take the inverse of both sides. So they undo each other, and we're left with sine inverse of x over 3 is equal to theta, which is the other piece of our puzzle. So let's fill these pieces in. So we're going to let cotangent of theta equal the square root of 9 minus x squared divided by x, and we're going to let theta be sine inverse of x over 3. So that our final answer will be negative square root of 9 minus x squared divided by x minus sine inverse of x over 3 plus c. All right, now this is what we're going to be doing for the rest of the example. Let me walk you through each one. This one, we're going to think about how we would set an ellipse. For the next one, similar to our previous example, to our first example, we're just using a different substitution. Here we see why we could be tricked using U substitution, which will result in an answer, but U sub would be better. Next problem, we continue using more trig substitution. Next problem, more substitution. Trig substitution, but we have to be a bit more clever because we don't have only a variable and a number. So we have to be more careful with our substitution. So for this one, what should x equal? How should you label your trig substitution? And then for our last problem, we don't have a setup, a traditional setup, right? We don't have a variable squared minus a number under that radical or in that radical. So because of that, we have to complete the square to make it look like something we want. Okay, these are our problems. I'll go over them in a second video. I just wanted to show you what trig substitution is and how it applies. I'll see you in part 2. Thank you.